Okay, good morning. My name is Joe Cho. I'm a technical account manager at Amazon Web Services. And this morning, I'm delighted to be joined by Keith Blizzard, Senior VP and Head of SRE and Production Services at Fidelity Investments. And in this session, we'll be discussing how Fidelity Investments builds and operates the most critical of applications at the highest resilience bar possible. I'll first discuss a challenge which probably many of you are facing, and which is why you're here. We have the onus to run the most mission-critical applications, 24/7, banking, trading, healthcare, government. And yet, things break around us, and sometimes within our own systems. How do we deal with this? The problem statement. And then I hand over to Keith, who addressed this problem statement by deploying chaos engineering at scale. And then I'll discuss how AWS Fault Injection Service, we partnered with Keith and Fidelity Investments to develop this platform. I'll dive deep into the actual functionalities and how we evolve both of our companies. And finally, I'll share some learnings and outcomes so that all of you here can benefit from what we've learned. So, the Enterprise Resilience Challenge. Let me begin with a little story, actually a big story. So back in 2019, Fidelity Investments migrated to AWS, the order management system. It's a core component of its trading system. It had a number of drivers. There were new market dynamics, such as fractional trades and zero fees, which increased trade volume. And also, if you remember around the time, there were all these game stock, meme stocks, which dramatically increased trade volume unpredictably. All this volume meant that the cost of operating the plant was in the foremost minds of many. And not just these things. The trading environment, its customers, the expectations were fast evolving. Everybody, every one of you, have a very sophisticated and powerful handheld device from which you can trade from. I myself, as an Amazon employee, we use Fidelity Investments as a personal finance service, so I myself am a customer. And also, while Fidelity is adopting the cloud, it still has very significant investments on-premise. So Fidelity wants to ensure that whatever it builds in the cloud also still services what's on-premise. The different lines of business, the different order types that are still on-premise. And most of all, trade continuity. So when the customer, such as like myself or many yourselves, press that button, we want to ensure that it happens and the customer has full confidence that it will execute. So capacity, scalability, cost optimization, speed to market, hybrid cloud, and foremost of all, 24/7 real-time operations supported by the cloud. These were the thematics that Fidelity was pursuing. And the services that you see listed here were what was used to address it. And so while Fidelity achieved these goals with these themes also provided new challenges, new things to learn. So as you saw in the previous slide, EKS and EC2, auto-scaling, provided the capacity, the cost efficiency. But that also meant that the team needs to now learn new things. How to manage cloud capacity, how to define memory allocations, scaling policies, retry policies, and sometimes latencies that occur. And speed to market. So Fidelity wanted its environment to be very agile in development. And we used serverless Lambda along with MSK for disconnected asynchronous architecture, which allowed for rapid development. But that also meant there were simply a lot more changes coming in. And each change, given the criticality of the application, needs to be carefully and thoroughly evaluated and tested. So more things to test. And then hybrid cloud. So new skills have to be learned. You are no longer close to the hardware. So things like optimization, experimentation, troubleshooting, skills need to be learned away from the hardware. And also, given the criticality of what this does, we chose multi-region architecture, which means that Fidelity now also needs to understand how to operate within a multi-region architecture environment. How does data sync happen in between? What happens as a hiccup? All these questions. So utmost of all, continuous resilience was utmost paramount. So I'm sure all of you guys know this code. We hear from Dr. Warner Vogel tomorrow. The fact of the matter is things break that we don't control. As a matter of fact, just a bit of an off script, some of you may have seen Will, the AV tech here, troubleshooting here a bit. Literally, 5 minutes ago, we had trouble with the setup. Unpredictable, right? So I was actually literally thinking about using my phone as a timer. These things happen. We don't plan on these things. And yet, although we don't control them, they impact our systems. And it's not just the things that we don't control. Some of these things we do control, namely changes. William Pollard, one of my heroes, he knows that without change, there is no innovation. You are here because you are here to innovate. That's what this week is all about. But the reality is, as you all know, change sometimes break our systems. So what are we to do? We can't stop change. We must take risks, as Swami had just said in this morning's keynote, right? So the problem statement, we have these host of events which we don't control, which can break our systems. And we have another host of events which we do control, changes, but they can also break our systems. What are we to do? How do you guys sleep at night? Hopefully not with a pager next to your head. Another very famous quote, which I'm sure all of you are familiar with. The ancient Chinese general notes, if you know your enemy and you know yourself, you need not fear the result of 100 battles. But this morning, let me reread this from the perspective of resilience. If you know your failure modes and you know your system and its dependencies, you need not fear the result of 100 incidents. If you need to go to another meeting, this is all you have to really keep in mind. This, to me, is resilience. This is chaos engineering at its core. So we cannot stop those events that impact us, like this thing breaking in front of me like 5 minutes before the session. But we can learn its dependencies, like what those events mean to our systems. And change, we certainly cannot stifle change, or we quickly become irrelevant. But we can understand what that change means to our systems. So by doing so, I can't promise that you'll get rid of all incidents. But I do believe that the incident bubble will shrink. The continuous resilience cycle. I think many of you already practiced this. This is the IT as we operate today. You set objectives, you design and implement, then you evaluate and test what you have built, you operate in production, and as you operate in production, you learn something new perhaps, and then you respond what you have learned, you build what you have learned, and the cycle repeats. With respect to operate and respond and learn. Just a few weeks ago, we had the US presidential elections. What a time to be alive. And perhaps during this event, given the market volumes that you saw, you realize that your scaling policies may have not been quite up to par. So you may have had a post-mortem, an RCA, root cause analysis. An RCA, not to blame, but to understand what the gaps were, so that you can build against those gaps, so that that doesn't happen again. That's a good thing. You learn from these things, and you should continue to do so. But the challenge I have you today is, can we shift left? I realize that's a terminology that comes often, but literally here, shift left, earlier in the resilience cycle. That learning that we just described, can you do that in that highlighted part? Evaluate. before app happens in production. And that is really the essence of chaos engineering. You see, as chaos engineers, I like to think of us as scientists. What do scientists do? We study, right? We study a system. If I was a biologist, I may be studying some agent in the lab. As technologists, we study architecture or applications. The biologist may use a microscope to study. Our tools of observability are things like CloudWatch, CloudTrail. And as scientists, we hypothesize. What happens if I have a scaling event such as the US elections? Will my node scale properly? I think so. I think my customer will be OK. But all that I think, we're not certain. And that is what we scientists do. We pursue the unknown. And it's not to be confused with testing. See, testing is validating what you already know. So the node scaling, OK, if I have additional node, I think I have additional scale. We check. That's good. And resilience testing is something you should continue to do. But, OK, it scales. But now what? How does it impact my peripheral systems? Are there any gaps? Those unknowns are what we're after. Those are experiments that we want to do against the hypothesis that we create. And also, we are responsible scientists. So back to me being a biologist. Perhaps the thing I'm studying in the lab is dangerous. Like it's a viral agent of some type. Then I certainly don't want that experiment to get out of hand, right? I don't want to create the next zombie apocalypse, okay? Well, chaos engineering, what are we doing? We are literally breaking things. So it can be inherently dangerous. So same thing. We want to build our experiments so it has proper safeguards, guardrails, okay? This is great. But where do you even begin, you might say? What experiments do I perform? Fortunately, we have this useful construct known as failure mode effect analysis, commonly known as FMEA. My understanding is that this stems from the manufacturing sector and that it is decades old. But it's tried and true, and it still holds value today, even in our cloud computing platforms. Now, this is probably another talk in itself, another hour. So I'm just going to touch the gist of it. But essentially, you go to your system, and you identify each of the functions in your system. And you think about what the failure modes are. How can my function fail? And with each of these failure modes, you think about what is the effect, impact, and the severity of that impact. What can cause this? And what's the occurrence, the probability of this happening? And what controls, detection, auditability do I have for this failure mode? You do this analysis, and you determine the risk priority. Let me give a quick example to make it clear. So let's say I have an update function. I think about this. How can my update function fail? Okay, perhaps it can outright fail, no update. What's the severity of that? From scale to 1 to 5, with 5 being the worst, well, the function literally failed to do what it's supposed to do. So that's pretty bad. Severity 5. How else can it fail? Well, maybe my function updates, but it's a little bit delayed. Okay, what's the impact of that? Well, I have a real-time system, so this is pretty bad. I could have potentially out-of-sync data downstream. So I think severity there is also 5. Now I think about the causes. What can cause these failure modes? For the update failure, perhaps I hit some throttling limit, right? Okay. Well, what's the possibility of that happening? So you think about that. Well, I'm actually a avid consumer of AWS Trusted Advisor. I keep track of that. Plus, my TAM is always yelling at me about my SLRs and whatnot. So I think the probability of that happening is actually fairly low. I'm covered. What about the delayed response? What can cause that? Well, this is actually a Lambda function, and perhaps I didn't allocate enough memory to my Lambda function, so it's a little bit slow. Okay? What's the probability of that happening? Well, actually, I rigorously tested this thing. I know exactly how much memory it takes. So this is this is resilience testing, not chaos experiments. I tested this thing. I know exactly how much memory this takes. So I think the probability of this happening is also pretty low. Okay, then I think about my controls and detections. So the update completely failing, okay? How well can I detect it? Well, I mean, this is pretty straightforward. I mean, I have a little try loop, and I look for an error code, say 500. I put into a retry queue. I think that's easy enough to detect. So the risk there is just a 1. But now, what about the delayed response? Well, my return code is 200. I actually get a good update. It's just delayed. I'm not quite sure if I have good ways of detecting this. It's probably some sort of a after-the-fact audit kind of thing. Not so great. So severity is a 4. So I do this analysis, right? And actually, this is like the simplified version. If you're more mature about this, the additional fields, like dependencies and owners. And I would ask that you do this as a team. Take a day and do this as a team. And I believe you'll have 2 outcomes. First, at the end of the day, your team will have a much deeper understanding of your system. And it'll be a communal understanding. You will all be on the same page. And also, at the end of the day, you'll have this nice artifact of all of your functions and failure modes risk prioritized. That is your resilience program plan. So this sounds all great, but some of you guys are thinking, this is kind of a academic, pretty colors, maybe nice content for some LinkedIn blog, but how practical is this? Well, Fidelity Investments has deployed this at scale. So without further ado, please allow me to welcome Keith Blizzard.
Oh. Thanks, all. Thanks for coming in. I love reInvent. This is my 11th one. And each time I come, I get to make great connections with people. You learn a little tidbits. And so today, we wanted to share a little bit of the how and the what to the why that Joe just went through, right? So if you think of the overview he mentioned with respect that everything breaks, he's right. I've been doing cloud computing now for 15 years. I could tell you with all the different issues, outages, and so forth, it does happen, right? So the most important aspect is how do you prepare, and also how do you build the practice at scale to be able to understand how your systems will interact. And I love this slide from Gartner. I stole it. I did reference it, so it says from Gartner and so forth. Because a lot of times when people, especially senior leaders, when you talk about cloud outages, they think it's that bottom left, that the whole cloud goes down. Knocking wood to everybody in the room. That doesn't happen. Like that would be a really bad day in everybody's daily life here and so forth of it. We do have regional failures, right? And some of them have been extremely painful over time, right? So a lot of the different components as part of the keynote yesterday was how do you build regional resiliency? So Amazon's spending a lot of time in enabling that natively in their products to have active, passive, really great regional failover capabilities in their PaaS. Where I try and drive across Fidelity, and I recommend for everyone else, is the circle on the right, the big circle. These are components and areas and so forth that the FMEA analysis that Joe just talked about are areas to understand and start building out controls in order to drive the resiliency across the environment. And what we're going to spend a little bit of time today is like, okay, well, why are we doing this now, right? What does it mean with respect to us and how it changed? So if you take a step back for us, we've been leveraging cloud now for 8 years. This has been an amazing journey, for at least my time here at Fidelity. The technology, the focus, the importance of the cloud transformation has been critical to the success of it. But if you look back at the history of Fidelity and the fact that we are a tech company with respect to just the financial services world, we used to build the resiliency in the hardware, right? We used to have really great systems that were based off of infrastructure level resiliency and harden it as much as possible, right? As we moved to the cloud, we had to change that mindset. because to Joe's point, everything will break, everything will fail. There'll be different components, whether it's latency, EBS failures, RDS failures, IAM failures, they will happen. And so, as we've gone through our journey, we're at a very large scale. 75% of our total application population now in the public cloud, 1,800 individual AWS accounts across the environment. But what I love is the bottom two numbers. So out of our critical systems, we set this up as a guideline of, yes, you should be doing different levels of chaos testing that I'll talk through about from a maturity perspective and execute them during your regular release process, right? So that's where we're going to spend a few minutes today talking about how did we do it. And then I'm going to hand it over to Joe, who's going to go through some actually of the partnership that we did in general to enable more faults in order to cover some of our scenarios and so forth. So if you start this, I always like using maturity models as a way to start the dialogue, right? And it's not about being able to judge individually where you are, but talk about what are the different phases you want to go up, right? So many people, especially as you start in a transformation from on-prem to public cloud, you'll start at that kind of level one, where, yeah, we need to plan, once a year, twice a year, do failover testing and so forth with respect to components, and that's usually the good or what we call happy path. Like, yeah, we have all the different components, we have the teams engaged, and we're going to practice just to make sure we could go. The phase that we've transitioned over the last few years is driving to level 1 and level 2 level, right? So with the infrastructure level faults and being able to execute them and make it easy for teams to accomplish that tasks in combination with your application level faults themselves. Do you have the right level of retry logic? Do you have the right threshold and limits across an ecosystem? Right? Many of the applications that you'll see in a couple minutes when we go through an example, they're not just a single app to database. It's a cosm of 10 to 100 microservices connecting with each other and understanding across a business process flow where that lives. And if one of those microservices is impacted, how does that affect the overall business process you're supporting? What do your customers actually see, and can you actually recover effectively? And so as you go up the stack with respect to the maturity levels, that's what you want to start trying out. So you might start off at an individual squad, but over time you want to go to that squad model looking across a business process flow, right? So how do you do that? How do you actually accomplish that task? We built a system, which we call Chaos Buffet, I don't know why we actually call it Chaos Buffet, but I thought it was an interesting term and so forth, where we're abstracting a number of the different types of ways to execute those faults. So whether I'm leveraging FIS, which Joe's going to spend some time on today, or other open source type capabilities, we're able to, in the CI/CD pipeline, execute these faults through common experiments and templates in order for us to actually drive the repeatable use across the environment itself. Not every developer needs to be an expert, right? How do you drive that repeatable nature, those common templates, as a way to understand and just give the development teams and squads the configuration profile that they want to test against? So if you look at this, we had to build a mechanism, right, that works across multiple public cloud as well as on-premise, but be able for us to drive that execution that allows us to accomplish that task, right? And many of you are probably in the same boat, right? So if there's ways and so forth that we could help even share some of those ideas, we're here. This is kind of a journey that a lot of companies are going on. For us, this is what allowed us to take that decision-making away from those individuals. So if you think of what a squad would need to accomplish, is really just filling out the configurations on the right side of the experiment itself. What is the observability link associated with the app to understand whether the success, the failure, the response time of that application is running as appropriately? What is your thresholds, right? How do you combine this with your performance engineering and performance testing scenarios to drive load in the system at the same time you're executing those chaos tests themselves, right? It's merging those components. And you do it across two different aspects. One is the faults that Joe talked a little bit about before, but also across the individual services. So for this to work, you need to be able to have the right level configurations of what testing of faults to those services. And that's actually where the partnership between us and AWS has been extremely strong. We've given them a number of the different services we needed in order to actually test out the systems. So when FIS and they're doing their roadmap, we are giving them the feedback and guidance like, we need this, and this is why. This is the type of faults we want to leverage and so forth of it. So if you look at the system and so forth that Joe talked about before, which is our order management system, you can see the logical architecture here of a highly available multi-region, multi-AZ transactional system, right? A lot of time and effort is spent in the beginning to actually configure the architecture and set this up effectively well, right? And so you see the best practices with respect to that, with the regional, the recovery, the Kafka queues, and making sure that we could actually have all that data. What was missing for us, and last year at reInvent, this was the conversation we had with the team, was we didn't have a way to test Lambda. And I really love Lambda. Lambda has been one of the great capabilities that Amazon went live with 10 years back, that allows us to be able to just execute code and drive those changes. But it was really hard for us to include a fault natively in that service without updating the code. We didn't want to factor any libraries themselves into the code itself, but allowing us to be able to test the system. Because in a system like this, Lambda was used to be able to synchronize the data. So if Lambda had a high error rates or was down or high latency, we needed to understand from the business process flow what was actually going to be affected and so forth. So that's been the partnership, that's been the area, and actually with that, Joe's going to talk about what AWS has done in order to help support this.
Thank you, Keith. So as you saw, AWS Fault Injection Service was a core partner and a core component of what Fidelity's built, the Chaos Buffet. So, the Chaos Buffet, the system that Keith just showed you, it allows any number of experiments, those experiment templates that you saw, for any number of applications, such as the trading system that we mentioned before. And these particular experiments, this is hardly an exhaustive list. This is just like representative list that's actually applicable to that particular trading system. I mentioned before the EC2 EKS account for capacity. So we have some EC2 and EKS experiments. Keith showed the multi-regional architecture with the Dynamo global table. So we have some pausing replication experiments as well. And also as highlighted, Lambda. So that earlier FME example I did with the latency, that wasn't just an example. That was the actual use case, which, as Keith noted, a roadmap item that we worked with together. So as Keith noted, this time last year, Lambda was not a natively supported service within FIS. So we thought about how to build this. Now, Lambda is also one of my favorite services. To me, it's the epitome of cloud computing. Serverless computing, code as a service, function as a service effectively, is code. And if you think about it, as with any code, there's generally two layers, right? There's the part that has the foundations, the libraries, the configs, the assets, and you separate that away from the business function. You do that with any code, right? And we do in Lambda as well. And Lambda happens to have a very useful construct which allows exactly this, aptly named the Lambda layers. So you put the configs, the assets, whatever you want, into the Lambda layer, separate from the actual business code. So this allows not only the clean separation, but also makes the Lambda layer portable across different functions. This is great. So we thought about, OK, where do we inject faults? As Keith noted, we want to keep the faults separate from the actual code. Invent and simplify. It's my favorite leadership principle here. It's the simplest of the solutions, but effective. We simply put the Lambda fault into a layer. So one of the use cases, as Keith noted, is latencies, right? This is a real-time trading system. How do we emulate latencies? It's literally a simple sleep function. Once again, invent and simplify. So we put that Lambda fault, the sleep, or we have other faults as well, such as the output. It's the same exact process. But for the next 10 minutes, I'm going to talk about the latency emulation. So we put the Lambda fault into a layer like this, and we had the actual business functional code separate. So what have we accomplished here? Now we have a parallel pipeline. So you don't have to do this. Like I could have literally had that sleep function in my code directly, right? Or do my insert, my chaos lib, chaos monkey, whatever into the code. You can do that, and that will emulate latency. But now then your code gets all messy, right? And God forbid that you push that into prod before removing the chaos and fault. OK, time to write up my resume if that happens. But this way, we have two parallel processes, the actual functional code, and also now the chaos development as well. Incidentally, that particular fault that I showed you with latency, it's not GitHub, AWS samples, so please have a look. It's very simplistic, and it works. And there's other Lambda layers and other faults as well, so please have a look. So I'm going to dive one layer deeper of how this exactly works. And it's very, very simple. So first, I create the Lambda package. And all it is literally that fault, whether it be a sleep function or whatever else you want to emulate into essentially a Python package. Step one, then I publish the layer. Simple CLI command, Lambda CLI command. And once I do this, it's an AWS resource. It's got an ARN, it's subject to IAM. So now I can distribute this, right? And then when I want to begin the experiment, I call the Lambda CLI API again. I attach the layer. I do my experiment. Once my experiment is done, I call the CLI again. I remove it. Simple. So this is your ad hoc chaos engineering experiment that we've been talking about. But we are an enterprise. We want things that are repeatable, curated, automated. AWS Systems Manager, commonly known as SSM, allows exactly this. Now System Manager, that's another section in itself. It has many functionalities and capabilities. But in this context, we want to stress the automation aspect of it. The screenshot on the right, I don't expect you to read this, but that's an SSM document, a runbook. It allows various parameters, including the scripting aspect. So in that scripting part, I'm literally just doing that third step I just showed you, calling the Lambda API to attach and then remove the layer. It takes expected parameters for the experiment, the latency, literally how long the sleep function runs, the Lambda layer that I created before, and the target Lambda function. Now we have a chaos engineering experiment. And now you can distribute this SSM document to your team. But we can go even a step further. FIS. FIS supports our services in two different ways. There are the natively supported services, things like EC2, RDS, EKS, which FIS can call directly. But FIS can also call SSM. And as you've seen, SSM is a very free-flowing, scriptable environment. So that is what we did. So we literally have an FIS experiment. And here I have a simple console view creating the experiment, which calls that previous SSM document, which I just showed you. Call the same parameters that the SSM document needs, takes the input, done. Now, some of you are asking, why are we doing this? Can't I just call the SSM document? You certainly can. But now you have a managed chaos engineering platform. FIS is tightly integrated with CloudWatch. Remember, once again, we are scientists. We need to observe and collect data. Back to that biologist that I mentioned at the beginning. Suppose he does all his experiments, but then takes no data, takes no notes. What's the purpose? With the tight integration, that FI has with CloudWatch, you collect all that data. A few slides ago, that Keith showed you when he showed Chaos Buffet, on the upper left, there was a data collection piece. That is key. Your data is gold, as you have seen throughout the week. And also, remember, we are responsible scientists. We don't want our experiments to get out of the lab. No zombie apocalypse for us. FIS also allows for stop conditions. A stop condition is a simple CloudWatch alarm. As you guys probably know, CloudWatch alarms can be triggered by any number of things. Node counts, CPU, memory, whatever. So you set that stop condition in your experiment, and that is your big red button to stop the experiment. So now you have a fully curated and a responsible chaos engineering experiment. So what have we accomplished here? So when Keith and team asked how to do chaos engineering experiments with Lambda, this is essentially what we delivered to them. This is roughly Q2 of this year. So now Keith's team, the Chaos Buffet team, they create that Lambda layer, okay? And then they also create the SSM document and manage it. And now their developers have access to all these experiments. And as you've seen from the YAML, the template files, the developers can define their experiments. That experiment is sent to Chaos Buffet, which calls FIS, which calls SSM, which does experiment. This is great. But this is still a lot of work. If you think about it, I mean, Fidelity has to manage and create the Lambda layer and also the SSM. So they asked if we can make it even simpler and more efficient. And as you've seen from this week, all of our product evolutions are largely driven by your requirements. So we did exactly that. We made FIS support of Lambda native as of October this year. Actually, October 31st, literally Halloween. And now, all you really need to do is call an FIS experiment, and all that I have described to you is already done. And if you want, you can still use the SSM document. In fact, that's literally still what's happening underneath the covers, right? Especially if you want to modify your experiment or create your own, you can certainly do that. But now, if you just want to do like Lambda faults, especially latency, and also like output kind of experiments, it's like all natively supported. So what have we accomplished here then? We have now created essentially a library of experiments that are centrally developed, managed, governed, validated, and safeguarded. So now some teams who may want to do chaos engineering but didn't have the resources at the time can use this. Or some other teams who may not have the experience or a little squeamish about running things can safely adopt this platform. And as you've seen from Keith's previous slide, we just enable so many application teams, and more than 3,000 applications are now using the system as Fidelity experiments. So that's great. So this is quite an achievement. 3,000 sounds great. But remember, once again, back to being a scientist. We can do all the experiments that we want. But if we learn nothing from our experiments, then what have we accomplished? So let me now share some learnings and outcomes. So all the learnings that Fidelity has achieved through this process can be largely bucketed into these 4 areas: surviving failures, system performance, matching demand, reducing impact area. Or technically, retries, memory allocations, scaling, and timeouts. And if you look at this, right, these are largely thematically configurations, right? So back to that continuous resilience cycle that we were sharing in the beginning, right? So suppose in that cycle, you're asked, and you're in your companies, you're deploying a cluster, okay? And you need to figure out the auto-scaling policies. What scaling policies do you put in? What numbers do you actually put in? Well, you might consult the best practices. You have some experience with the system, so you do some math. You might call up your favorite SAR TAM, keeps me employed. But ultimately, what you're first pushing out to prod, it's a bit of an educated guess. And it's not until your system, those numbers hit prod, and you have something like the US elections, that you really zero down on what those numbers should be, right? But remember, we want to shift left. So what Fidelity has achieved by doing chaos engineering at scale was come to those realizations before they happen. And also, if you look at this, right, a lot of these experiments and outcomes, they're very practical. These are not just academia kind of things. I mean, these are retries, they're very practical things that you would apply in your system. How did Fidelity know which experiments to do? Well, they practice FMEA, as we said. So they were able to zero down in their roadmap exactly which gaps to pursue, which unknown unknowns to pursue. And you can see the results. So if you are deliberate and specific in your resilience engineering, you achieve results like this. As an IT professional, a graph like this should make all of you smile. So this is the yellow line is chaos engineering coverage at Fidelity Investments. The pink line is MTTR, mean time resolution at Fidelity Investments. And you can see the dramatic impact that this has had. And actually, looking at this, it should be even more pronounced. Because as this was happening during the year, Fidelity migrated more applications to the cloud. And yet, MTTR is still going down. Now, I can look at this, and I think we should certainly be happy about it and congratulate ourselves. But back to that William Pollard note, and what Swami noted, we want to continue to innovate. We don't want to just stop at our laurels and be comfortable about it. We want to continue to learn. So what are we going to do next? That yellow line, we want to achieve 100% chaos engineering coverage. Every single application, we want it to be covered. And not just broadly, but also depth, in depth. So we talked about Lambda failure mode in particular, right? But your system has many, many more failure modes. So we want to partner with Fidelity further and all of you further to understand and develop more failure mode capabilities. Because per the Sun Tzu code, the more failure modes that we understand, the better we're prepared. And also, increase chaos maturity across the different teams. We want to democratize what we have learned, democratize this process. In a large organization such as ourselves, you have different teams with different maturity. We want to ensure that every application team has a graph like the one I showed you before. And let me now end this with something more candid. So as a TAM, I serve the financial services. And prior to coming here, I've been in the financial services my life, a bank, hedge funds, and whatnot. There's a bit of a notion within the financial services that chaos engineering is not for us. Maybe it's for like media, entertainment. I mean, after all, Netflix, those guys, they pioneered the space. By the way, thank you, Netflix, wherever you are in these halls. Thank you so much. But you're thinking, okay, but I run trading and banking, asset management. Can I really do this? Well, I would argue that we, who have the most austere resilience requirements, that are regulated, as many of us are. And our applications are not just random business applications, but they serve societal functions that run the global economy. So I would say, actually, the responsibility is on us to not just make chaos engineering and these kind of practices something suitable that we do, but they should be foundational. Okay. All right, thank you.